As we dive into our next session, let's remember what Carl Sagan once said. Somewhere something incredible is waiting to be known. Our next speaker is Kabir Sahni, a high school student with exceptional skills in mathematics and public speaking. His co authored research is published in the NCERT affiliated Journal of Education, and he founded Mathematics and Vision Ed to support blind students with EcoMath, an AI chatbot funded by a Forbes recognized entrepreneur. Let's welcome Kabir Sahni to the stage.
How many of you have used AI? How many of you have used ChatGPT or Googlebot? Everyone, right? Since it has come, each one of us have tried it, used it, and perhaps bookmarked it on our computer screens. But I pose one question to you. Is AI even nearly as good at answering math questions as it is at generating and writing stuff? All of us know it is fantastic at writing stuff because at some or the other point, we have used it to write our mails or send out formal messages, right? But is AI good at answering math problems? Let us ask an LLM two questions. Let us use an anecdotal evidence. I asked ChatGPT to compute the remainder of this complex problem. Here is the solution. Now I have two questions for you. Does the answer seem correct to you? Yes, it does to me. Is the answer actually correct? Yes. So AI is good at answering math problems. Just to double check our hypothesis, let's ask it to compute the answer of another question. It gave us a long solution. Again, does the answer seem correct to you? Yes, it does to me. But is the answer actually correct? No. Let us come back to this question in a moment. But before that, let us understand what AI fundamentally is through this example. If you look up on Google, you'll see that AI is a technology that mimics human intelligence. So in layman terms, these LLMs like ChatGPT or Googlebot, they are nothing more but a guessing machine. They produce an answer that looks as close as to the real answer. Therefore, even if the solution is wrong, like it was in this case, it will seem correct. Now, coming back to our question, is AI good at answering math problems? A few months ago, every mathematician, every researcher would have said no. Why? Because complex math problems, they require you to form and draw on abstractions, which AI models were not good at. The reason being because for every machine learning model to function well, you need to train it on large sets of data. And when it comes to data in mathematics, there's a scarcity of it. Now, all of you might be wondering that on the internet, there are tons of math questions. Then how is there a scarcity of data? Well, let me rephrase. There is a scarcity of math data in the formal language. For an AI model to understand math questions better and to essentially verify its answers, the math questions need to be in the formal computerized language, whilst all the data available on the internet is in the informal language. That is exactly the reason AI was not good at answering math problems. But quite recently, the Google DeepMind, it introduced a model called AlphaProof. AlphaProof is an AI model that tackles complex math problems. But how did they do it? Now, if you enter your problem in this model, it first converts your problem from the informal language to the formal language so that AI can understand it. And once it has generated its answer, it is going to verify its answer through a proof assistant. Now, what is a proof assistant? Think of a proof assistant as a software that contains all the mathematical knowledge. Now, if you are inputting any mathematical solution, any mathematical proof for that matter, it is going to tell you if it's correct or not. Let's say if at any point of time you have written 2 plus 2 is equal to 5, it is going to point that out because it has all the mathematical knowledge. So essentially, after generating the solution, the AlphaProof verifies its solution through this proof assistant and then it gives you an answer. With the introduction of AlphaProof, the Google DeepMind also introduced another AI model called Alpha Geometry 2. It is again an AI model, but specifically designed to tackle complex geometry problems. Now, to assess its competence, the AI models were given questions from the International Math Olympiad. There were 6 questions, and together the AI models were able to solve 4 questions, which is an impeccable score of 28 out of 42 in the International Mathematics Olympiad. If a human would have scored that, they would have bagged a silver medal internationally and would have missed a gold medal just by 1 mark. This is the power of AI. This is both surprising and a huge leap in technology. Now, let's change our question. From is AI good at answering math problems, which I feel we have answered to a large extent, to how has AI impacted math? But before we answer this question, let us understand what math is. Is math just about solving complex problems? Oh my God, you solved this complex problem, you are a good mathematician. Most certainly not. Math is also about the flow of new ideas, the flow of new theorems. Like any other subject, research is a fundamental part of math. So now we have moved from understanding these complex theorems and complex problems to creating and proving these complex theorems. Any theorem or formula that you have studied, right from Pythagoras' theorem to the rules of integration, they have been proved by mathematicians. But how did they prove it? Did they have an epiphany one day and they wrote the proof? No, most certainly not. The first proof that mathematicians write is in the informal language, which is to say, it consists of certain ambiguities and loopholes. Now, if you are studying something, if a proof has to be finalized, it cannot have any loopholes, right? So after the proof is written, it needs to be formalized. Formalized, now what do I mean by these terms? Let us take an example. Look at the first statement. The sum of 2 odd numbers is always even. You get the idea of what I'm trying to say. It is mathematically correct. But if you ask a mathematician, they are going to say it lacks mathematical rigor because there are certain ambiguities. So after the mathematician formalizes the proof, the statement is going to look something like this. Let A and B be 2 odd numbers. Then A is equal to 2k plus 1 and B is equal to 2m plus 1 for some integers k and n. Therefore, a plus b is equal to 2 into k plus m plus 2, which is clearly even. Now, the second statement has mathematical rigor. It does not have any ambiguities. But the problem with formalization is that this is a tedious process. In fact, it is more time consuming than writing the proof in the first go. Therefore, it often takes years to formalize the proof. If we look at the timeline of conjectures being resolved and then being formalized, we'll see an interesting pattern. The four-color theorem, which is a very famous theorem, it was proved in 1976, but it was formalized in 2005, which is to say, for more than 20 years, mathematicians were iffy about its proof. The Kepler's conjecture, it was resolved in 1998 and formalized in 2014. The liquid tensor experiment, it was proposed in 2020 and formalized in just 2 years. And quite recently, the polynomial conjecture, it was proven in November 2023 by Terence Chow and a group of mathematicians. It was formalized in just 3 weeks. If you see, the time period of formalization has gone right from years to weeks. This speed up is owed to the introduction of modern technology like GitHub and libraries. In earlier times, whenever we need to formalize a proof, you need a new set of eyes. You need to work in groups because whenever we are talking about long, rigorous proof, you need another set of eyes to identify the loopholes and fix them. But back in the 1900s, mathematicians didn't used to work in large groups because if some other mathematician is working with you to formalize the proof, you need to trust their mathematical ability completely. However, today, mathematicians are working in groups of hundreds and 200s. Why is that? This is inherently because of the introduction of modern technology. Today, mathematicians do not write their proofs on pen and paper. They write it on computers, and the proof assistants tell them if there is any problem. The conjecture that was proven by Terence Chow, in that group, there were a couple of computer scientists as well. Imagine if Terence Chow proved this conjecture back in the 1900s. Do you really think computer scientists would have been involved? No, mathematicians certainly wouldn't have allowed that, right? Currently, AI can help fill in one or two lines of proofs. However, the prospect seems very bright to the point that it would be able to write bundles of lines of proofs. Now, when we talk about math, a large part of it is the pre-formalization stage, which is to say, thinking of proofs, thinking of the Pythagoras theorem and essentially proving it. Now, I'm sure many of you might be thinking that AI cannot possibly contribute to new research. Let me burst the bubble. It can and it has. Think of AI in this scenario as a guide dog for a visually impaired person. The visually impaired person knows where to go, but they aren't able to go there themselves. That's essentially where the guide dog helps them. But just like a guide dog, AI isn't a magic machine. It needs to be trained. So essentially, when mathematicians know that, okay, over here, there is a certain relationship, but because of the complexity, they aren't able to figure it out, that's where AI helps them. So essentially, where the intuition of mathematician ends, that's where AI commences to think. Let us take an example. In topology, which is a pure mathematics field, knots are quite extensively studied. Now, think of mathematical knots as simple knots only. Like when I'm tying my shoelace, I'm tying a knot, right? Now, in topology, mathematicians are interested to know the properties of these knots, to know if two knots are similar. Which is to say, if I am tying my shoelace, I am tying a knot, let that be called knot A, and my friend, he is tying another knot on his shoe. Let that be called knot B. So mathematicians are interested to know if these two knots are similar, if they are equivalent. Now they figure it out if these knots are equivalent through a mathematical tool called invariance. Invariants are of various types. There are algebraic invariants, there are numerical invariants, there are geometric invariants, and they basically show if two knots are similar. Basically, if two shoelaces are similar, right? Now, mathematicians knew that there is some relationship between the hyperbolic invariant and the algebraic invariant of a knot. But they weren't quite able to figure it out. So what did they do? They trained a language learning model and they asked it to figure it out. Turns out, the language learning model essentially did it and it was accurate. This is the power of AI. Currently, AI cannot think of new problems. It cannot think of new conjectures, but it can certainly help mathematicians solve those conjectures, solve those problems. Hence, AI is a guiding light for mathematicians. Today, when you go home, I urge all of you to not just think about AI, to not just talk about AI, but to experiment with AI so that even you can figure out new things. Because essentially, when you'll experiment with AI, that's when you'll be able to carve a better future through AI. Thank you.